Look, please join me in welcoming. We have the distinct honor today to have Professor Sujata Bhatia. She is what I like to call, she's a physician, a bioengineer, a professionally licensed chemical engineer. She's what I like to call a text conference of one. Really, she teaches, so she's a professor of the practice of chemical and biological engineering here at Tufts, and she also is on the teaching faculty of biomedical engineering at that school down the road. I think it starts with an H. Look, you can't have school spirit here, you can't. But really, we're totally honored to have Professor Bhatia with us. She totally embodies so much of what Tufts, I think, has to be proud of, and therefore what TEX aims to promote. She balances teaching and research. She does theory and practice in pursuit of a better world. And tonight she'll be discussing with you the biomedical uses of sustainable materials in all around that world. So please put your hands together, and thank you so much for being here, Professor.
It is such an honor to be here. I'm so honored that of all the amazing, brilliant faculty at Tufts that you could have invited for this occasion, that you actually invited me. And so when I got the email, I was like, wow! You know. So anyway, I see some of my current and former engineering students in the audience, and that's a wonderful thing for me too. One thing I often say to my engineering students is that every time I look into the eyes of a student, I can see the future. And I think that's a beautiful thing, and it's actually very addictive for me. So today I'm going to tell you about my work with medical materials. My industry career was at DuPont. I spent 8 years at DuPont before coming to Tufts to teach. And so I'll talk about the work I've done at DuPont, and I'll talk about the work I'm doing now. And I hope to get you to think differently about medical materials and what is a life-saving material. So if I were to ask you, name a life-saving medical technology, you might name a defibrillator. You might name an EKG machine. You might name a pacemaker. And these are all life-saving materials. But you might not name silk, or corn, or soy, or sugars. And in fact, these also can be life-saving materials. And so I hope to convince you of that with my talk today. We are going to talk about sustainable materials as biomedical materials. And the great thing about using sustainable materials is that, number one, they work better with your human body, and number two, they enable the developing world to now participate in medical innovation in ways that were not previously possible. So you're going to get a little bit of an engineering education here today. When I look at the human body, I see polymers, okay? Now, the older folks in the audience may remember the movie The Graduate, right? Where Dustin Hoffman is about to graduate college, and someone comes up to him and says, plastics, the future is plastics. Well, I want to convince you that the future is biopolymers. Now, if you don't know what a polymer is, and many of my engineering students might know what a polymer is, right? I'm a chemical engineer. I see nothing but polymers when I look at the human body, right? A mechanical engineer might see, pumps and joints and, that sort of thing, but I see polymers. So what's a polymer? A polymer is a long chain molecule that's made up of smaller monomer subunits. So if I see my student Kevin Kozikowski in the audience, and he is a mono-Tufts student, but if I got everybody in the audience to hold hands, if you like, you could all hold hands, then I would have a poly-Tufts student, and so that would be a polymer. Okay, so DNA, RNA are polymers of see, I get really excited about this. They're polymers of nucleotide monomers. Polysaccharides are polymers of sugars, right? Proteins are polymers of amino acid monomers, and these are the body's major sources of information, of energy, of structure and function, right? So, given that our body's made up of polymers, and given that we are now at a point with our technology where we have this unmatched capability to produce natural polymers, to manipulate natural polymers. In fact, this is the basis of biochemical engineering. And at the same time that we have this capability to produce natural polymers, it makes sense to ask ourselves, could these polymers be used in medical devices? Because innovators in biomedical engineering are always looking for better materials for medical devices. They're always looking for more compatible materials for medical devices. Our bodies are not made up of metals. Our bodies are not made up of, electronics. Our bodies are made up of polymers. So that's something to think about. Okay. So in fact, the idea of using natural materials as life-saving medical materials is not new. The Egyptians were smart enough to figure this out when they used silk for sutures. They also used catgut for sutures. And I learned recently that even in ancient Egypt and India, there was the forerunner to the surgical staple. They would actually get a beetle to bite a wound and then twist off the head of the beetle and the jaws would stay in the wound, and so then you would staple your wound closed, okay? And what's amazing to me is that these natural materials are still in use. So, when I was on my surgery rotation in med school, surgeons were using silk sutures, and they were using, catgut sutures, and so these natural materials are pretty darn good. So, actually, let me tell you about a project I worked on for wound closure. So it turns out that sutures and staples are pretty darn good for closing wounds, but they're not perfect. You can still have leakage from these wounds. And so at DuPont, I worked on a team to develop these, polysaccharide-based tissue adhesives. Now, I can see people in the audience are starting to cringe, like, oh, she's starting to show chemistry. But all I want you to see is that this one over here, dextran, that's a big old polymer of sugar monomers. And we made this beautiful sealant with this dextran, and it's naturally derived. And so we were able to show that this polysaccharide-derived tissue sealant could be used as an adjunct to sutures or staples. It could also be used for trauma applications. So if you have an organ where you've kind of had a chunk of the organ kind of sliced off, this happens to motorcyclists all the time. I'm setting you up for the next slide, which is rather graphic, and I'll go through it rather quickly. But it could be used for GI surgery as an adjunct to suture or staples. Could be used for vascular surgery to attach vascular grafts, and even for ophthalmology, for cataract incision surgery, which is very, very, very common. The next couple of slides are graphic, and I will go through them very quickly, but I just want to show the surgical applications of this naturally derived sealant. Okay, so we have liver, bladder, colon, vascular graft. Very versatile sealant. Next slide. Okay, eyeball. Next slide. Okay. All right. So it's a very versatile sealant. And you can already see that you're solving all kinds of unmet clinical needs with this naturally derived material. Now, later on in my career at DuPont, we also were working with a corn-derived polymer called Serona. The sugar I just showed you was actually bacterially derived. And amazingly works very well with the human body. This is a corn-derived polymer, and it's got some nice mechanical properties. DuPont actually initially marketed this for carpeting, which is great. I mean, certainly there's, soft carpet is nice. But when you go out in the world, you should really think about what are the world's most pressing needs. And I think about medicine as a very pressing need that we need to meet. So what these very pretty green things are showing is these are cells with our Serona plastic and Serona film, all corn-derived. And, the cells look very, very, very happy. You don't need to be a scientist to see, boy, there's a lot of cells there with that. So that means that you could use this corn-derived polymer. So at some point I decided that I love students so much I was going to move from industry to teaching and working with students. So I got a hold of this corn-derived polyallactic acid, and what's cool about it is that you can make these little fibers with it. It degrades, it's biodegradable, it degrades to lactic acid. Even if you're not a chemist, you've heard of lactic acid. The body produces it. If you go for a run, your muscle produces lactic acid. So your body knows how to get rid of lactic acid, right? So it's a naturally derived material that degrades into something natural that your body knows how to get rid of. It's not foreign to the human body. And so you can use this kind of patch. Well, you could use it for a wound closure patch. You could use it for maybe you could use it for a cardiac patch for people who, are in heart failure. So in fact, I started working with a student, Leslie Ray, and Leslie started looking at this corn-derived polyallactic acid in contact with heart cells, these cardiac myocytes, and these are very happy cells. In fact, after 48 hours, the heart cells actually started to beat when they were in contact with this corn-derived material. So we were really excited about that. This is Moreji Futunde. Moreji is originally from Nigeria. And Moreji actually approached me about doing a senior thesis project, and she said, you know, I want to work on something that's going to help people in Nigeria. And so I said, well, you know, I've been doing this stuff with naturally derived materials. Would you be interested in this, Moreji? And she said, sure. And so this is soy and cotton fibers with corneal cells. And you know, you can immediately imagine some really interesting applications, right? So you could maybe use these naturally derived materials for corneal tissue engineering to regenerate the cornea, right? Regenerating part of the eyes. You need to have a nice polymer scaffold for that. I'll come back to Moreji in a second because she had a really good idea. By the way, I think that students are the drivers for innovation at any university, and so that's why I love working with students, and particularly the youngest students at the university. I love undergraduates. Okay, this is Godwin Abiola here, and Godwin was working with microspheres made from alginate. Okay, I'll sit here. And you know, this alginate is made from seaweed, and so you can make these microspheres and use them to deliver cells, use them to deliver drugs, use them to encapsulate electrically conductive polymers like carbon nanobrushes, and so you could use that to regenerate electrically conductive tissues. You can enhance their strength with another natural material called pectin. Now I know I've gone through a lot of stuff really fast, right? But hopefully I've convinced you that bio-derived polymers, either polysaccharides from nature, right? Like as we showed with our sealant. Polymers from corn, polymers from soy. I even had a student work on polymers from bamboo, right? Polymers from seaweed are versatile. They can be used for a variety of medical applications. You saw very quickly, you know, the eye, the liver, the blood vessels, right? You know, could even be used for the heart, could be used for all kinds of applications in stem cell delivery, in drug delivery, in tissue repair and regeneration. They naturally interface with human cells and tissues. Why? Because we're made of polymers. We are naturally, you know, not metals, right? And so you might not have as bad of a foreign body response when you use these kinds of materials. And they're tunable. You can tune them to meet the mechanical requirements of implants. So, you know, I told my friend Kalestos, who's at the Kennedy School of Government down the road, about this idea, and he got really excited because he's from Kenya, and he was like, wait a minute, like where I'm from, you know, agricultural polymers are all around us, so maybe this means we can contribute. So I actually gave a lecture via Skype to a group of PhD scientists and engineers in Kenya, and they got really excited about it. And tomorrow, I'm going to be giving a lecture via Skype for scientists and engineers in Nigeria, and they got really excited about it. Why? Because this can empower people who are in developing nations, empowering scientists and engineers in developing nations to join into the biomedical revolution, okay, to leverage their own capabilities. So what are we saying? We're saying that when we traditionally think about medical technology, we think about electronics and machinery, and there's nothing wrong with that. But sometimes electronics and machinery can be ineffective and inappropriate in the developing world, and we need to do more to build capacity there. So we're saying let's have a new definition of medical technology that incorporates not only electronics and machinery, but also bio-based polymers, because then you can have cooperation between the health and agricultural sectors, and you can have a two-way flow of innovation between the developing world and the developed world, right? So that we have to get out of this mindset that, oh, well, we come up with all of the inventions here and then ship them over to a low resource setting. Actually, folks in low resource settings are pretty smart people and want to leverage the resources around them to contribute to innovation around the world. Okay, so let's reframe the conversation. Let's adopt a new definition of technology, that technology is not just computerization, digitization, and building machines. Not that there's anything wrong with that. My brother's a mechanical engineer. My sister's an electrical engineer. But let's have a new definition where technology is really using scientific knowledge to make people's lives better. And it's not really a new definition. It's actually, let's go back to our roots as far as technology, right? Okay, and so I am both a doctor and an engineer, right? I'm a physician and a bioengineer and chemical engineer. And sometimes I talk to pre-medical students and they get this mindset, well, I'm a doctor, not an innovator, right? Well, so this is from Star Trek. Maybe some of you don't know what that is, but here's McCoy, and here's Scotty, and McCoy in a very classic episode called Mirror Mirror, they call on him to help repair the engine. He says, I'm a doctor, not an engineer, darn it. And Scotty says, now you're an engineer. So I want all of you to think of yourselves as engineers and designers. There's going to be a fantastic talk later on about design. You too can contribute to innovation. Anybody can have a good idea. Thank you for listening to my talk.